Hello and welcome to lecture 32. So, in last lecture we were discussing about this numerical. We have solved a similar numerical for the flying condition, and this numerical we are solving for the sea level condition or the ground level condition, and some changes here you can clearly see in terms of mass flow rate, in terms of bleed air tapping at temperature and pressure. No doubt the percentage extraction, that is what is similar. So, let us try to solve this numerical here. So, these all are the information which are available with us. Say my flying Mach number at the ground condition, it is given 0. We have our diffuser efficiency. So, we can calculate what will be say my exit temperature and pressure from the intake. Similarly, we can calculate exit pressure and exit temperature from the fan. We have our compressor from where some amount of air it is been bleeded, that is where we can calculate what will be our exit pressure and exit temperature from the compressor. For combustion chamber, we know what is our turbine entry temperature, the amount of say drop of pressure that is known to us. We know the bleeding, that is what we are doing from the compressor. We have information about the calorific value. So, we can calculate what will be the exit pressure and what will be the fuel air ratio. For turbine, we can do similarly calculation for exit pressure and exit temperature. For LP turbine also we can do calculation for exit pressure and exit temperature. We will be doing the calculation for critical pressure ratio for nozzle design or nozzle calculation, where we will be calculating exit static pressure, exit static temperature, and we will be calculating the velocities from the turbine nozzle as well as from the fan nozzle. And from there we can calculate what will be our performance parameters. So, rather repeating this all numerical again, let us check with your solution. So, here this is what we have solved in last lecture. These all are the exit pressure and exit temperature from all the components when we are considering that as a flying condition or the cruise condition. Now, based on the information given, you can do calculation for the ground condition. Just verify these answers. Are you getting similar answers or not? Just check with this part. Okay. And rather solving this numerical again for the ground condition, we will be focusing more in terms of discussing the effect of cycle parameters on performance of the engine. Okay. So, let us start with the comparison part. Here we are having this as our comparison. So, net thrust for the cruise condition was 17.48 kilonewton. For the ground condition, it is coming 126.2. We have our thermal efficiency for the cruise condition to be 30.34, and for the ground condition it is coming 29.25. Since for the ground condition my velocity is 0, that is the reason why propulsive efficiency is 0 and thermopropulsive efficiency or overall efficiency also will go 0. Okay. Now, let us try to do the discussion in terms of performance parameters. So, the performance parameter of our interest are thrust, specific thrust, thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency and overall efficiency. For this turbofan engine, it is mainly been depending on say overall pressure ratio, which may be fan pressure ratio, LP pressure compressor pressure ratio, HP compressor pressure ratio. Here in this case there is nothing called HP and LP compressor. So, we are considering compressor pressure ratio. We have parameter called bypass ratio, it also has impact on all these parameters. Here we have added with the bleed. So, we will be discussing what will be the effect of percentage bleed on the performance of the engine. We will be discussing about the turbine entry temperature, efficiencies of different component also plays important role. If we will be putting this for the discussion, it will increase the number of slides and it will increase the confusion to you, and this we have already discussed in week 2 what all are the effect of the efficiency numbers and from where those assumptions we are making with. Okay. So, what all numericals we have solved or we will be solving, all these numbers are standard numbers. Okay. So, mostly for the initial case, for the baseline design, for making the initial engine calculation, they are assuming these numbers. Later on, based on the experimentation for the fan, compressor, combustion chamber, turbine, even for the nozzle, they will be recalculating the efficiency, and those actual numbers they will be using for the cycle analysis and performance assessment. And here we are having ground condition as well as the flight condition. Okay. So, let us discuss first with the effect of fan pressure ratio. So, we will be varying the fan pressure ratio, compressor pressure ratio, turbine entry temperature, bypass ratio and mass flow rate parameter we will be putting as a constant. So, here in this case, rather discussing only for ground condition or only for flight condition, let us put this together. So, let us see, very first we will be discussing about the ground condition. When we are increasing our fan pressure ratio, we know in order to increase the pressure ratio, we need more amount of work. That means, my LP turbine will be generating more work or more amount of work will be absorbed by this fan, and that is the reason why my exit temperature will be lower. That is what will lead to reduce our V9, and that is the reason why our hot thrust, that is what will be decreasing with the increase of fan pressure ratio. Similarly, here in this case for the cold thrust, we know when we are increasing our pressure ratio, accordingly my exit velocity from the fan nozzle will be increasing, and that is what will lead to give the rise of our thrust. And in overall we can say this is representing with increase of fan pressure ratio we will be having increase of thrust. Now, here also we are having certain limitation beyond which we cannot go, because that is what is violating our second law of thermodynamics. So, that is what we need to realize and we need to understand. So, here we have not considered further points downside. Okay. The reason you can easily find out, you can do one calculation, you just take this fan pressure ratio as 1.7 and try to calculate and check what is happening. You will find my hot thrust, that is what will be going towards say negative value, or that is what will be going to 0. Why is it so? Just try to do the calculation, try to find the reason behind that. Okay. Suppose if we consider for the flight condition, we are having inline train where we are having hot thrust, that is what will be reducing with the increase of fan pressure ratio, and my cold thrust will be increasing with the fan pressure ratio, and in overall we are having our thrust to be higher. Okay. Now, let us look at for the specific thrust. Now, we are discussing this specific thrust parameter again and again. So, the question will come, what is our requirement? Do we want specific thrust to be higher or lower? What is our expectation? Are we looking for the specific thrust to be higher? So, what is the meaning of that? Okay. So, just try to find the reason. Here in this case you can say, since my thrust is increasing with the fan pressure ratio, that is the reason why my specific thrust also is increasing, both for the ground condition as well as for the flight condition. In the case here we can say we are having say reduction of thrust specific fuel consumption with the increase of fan pressure ratio. So, when we are talking about the fuel economy, it says by increasing the fan pressure ratio we are able to reduce the thrust specific fuel consumption, but that is what will be at the cost of increase of specific thrust. Okay. Now, let us look at what is happening with our efficiency. So, here in this case this full line, that is what is representing when we are having our ground condition. For the flying condition, with increase of fan pressure ratio, we have increase of our thermal efficiency, as well as we will be achieving higher propulsive efficiency. Okay. So, you must realize the reason behind increase of the fan pressure ratio and how it is affecting our thermal efficiency. So, thermal efficiency, we can say that is what is a function of my velocity, it is a function of my thrust, as well as in denominator we are having the amount of fuel, that is what we are inputting here. Okay. Now, this is representing the fan pressure ratio. Let us look at what is happening with changing the compressor pressure ratio. Here for this case, we will be putting our fan pressure ratio, turbine entry temperature, bypass ratio, mass flow rate, and bleed also we will be taking same. Okay. So, for that case, if we look at here, it says it is giving the similar trend what we have observed with increase of fan pressure ratio. We can say with increase of compressor pressure ratio, we will be having drop of hot thrust, and you will be having say increase or slight decrease of cold thrust, and in overall we will be having decrease of thrust with the increase of compressor pressure ratio. Again, in this case, we need to have more amount of work to be generated by the turbine in order to generate the compression ratio for this particular compressor. And here in this case, what all we are doing, it is at fixed parameters. The fixed parameters are fan pressure ratio, turbine entry temperature, bypass ratio, all these parameters are fixed, and that is the reason why we are having this kind of trend. For the case of our flight condition, we are having similar trend what we are observing from the ground condition. So, here in this case, with increase of compressor pressure ratio, we will be having decrease in specific thrust both for the ground condition as well as for the flight condition. Similarly, we will be having slight reduction in thrust specific fuel consumption. So, we can say for this particular parameters what we have selected, the increase of fan pressure ratio, compressor pressure ratio is not much benefiting in terms of say reduction of thrust specific fuel consumption. Okay. In line to that, here we can say this is representing our thermal efficiency and propulsive efficiency. So, we can say for the ground condition with increase of compressor pressure ratio, we are having increase of thermal efficiency. Similarly, for the flight condition also with increase of compressor pressure ratio, we are having say increase of thermal efficiency, even increase of propulsive efficiency, and in overall we can say we are having say overall efficiency also to be increased with the increase of compressor pressure ratio. Okay. Now, next important parameter we can consider, it is our bypass ratio. Suppose if I consider I am increasing the bypass ratio, so you will be having effect on both the thrust in terms of say hot thrust as well as cold thrust. And interestingly, here if you look at with increase of your bypass ratio, we will be having decrease in hot thrust. Okay. Here in this case, this is in line to what we are talking about the core mass flow rate. Okay. So, bypass ratio we are defining in terms of fan mass flow rate divided by core mass flow rate. So, with increase of bypass ratio, we can say we are having the fan mass flow rate, that is what is increasing, that is the reason my cold thrust it is increasing. Similarly, because of increase of my bypass ratio, my m dot core, that is what will be reducing, that is what will lead to reduce my exit velocity, and that is how we will be having the reduction in thrust. So, in overall net thrust for the ground condition, we have reduction in the thrust. There is not significant effect we can say for the flying condition. Okay. Here in this case, it says my specific thrust, that is what will be reducing with the increase of bypass ratio. Okay. So, in this case we can say with the increase of bypass ratio, thrust specific fuel consumption is reducing. So, when we are talking about the fuel economy both for the flying condition as well as for the ground condition, by changing bypass ratio we are able to move towards the good say specific fuel consumption, or we can say we are moving towards the fuel economy, but that will be at the cost of reduction of my specific thrust. Okay. So, we will be discussing all these parameter again when we are targeting something new. Okay. At this moment what all calculation we are doing, based on that we are making these discussions. Okay. Now, here in this case it says by changing the bypass ratio, our thermal efficiency, that is what is increasing up to some extent, and then after we will be having reduction for the ground condition. So, must realize here what we mean by increase and decrease of thermal efficiency, because that has direct impact as we have discussed in terms of my exit velocity. Okay. So, here in this case for the flight condition, our propulsive efficiency is increasing, thermal efficiency also is increasing, and we have improvement in overall efficiency. So, let us see what next we have is in terms of our turbine entry temperature, putting all other parameters to be constant. When we are putting these parameters to be constant, let us look at what is happening. With the increase of turbine entry temperature, our amount of hot thrust, that is what will be increasing. It is but obvious, with increase of turbine entry temperature we will be having, in order to achieve this you need to have more amount of fuel to be added, your exit velocity also will be higher. It has not impact on the cold thrust. With increase of turbine entry temperature, our net thrust, that is what will be increasing both for flight as well as for the ground condition. And since my thrust is increasing, so specific thrust value also will be increasing. Let us see what is happening with your thrust specific fuel consumption. Any guess? So, let us try to understand what will be the impact of turbine entry temperature on our thrust specific fuel consumption. So, here it says what will happen when I am increasing my turbine entry temperature, the amount of fuel I need to add in order to raise that temperature will be higher. So, where will it be impacting? It says with increase of turbine entry temperature, we will be having thrust specific fuel consumption, that is what will be increasing both for ground condition as well as for the flight condition. Okay. Now, let us look at what is happening with the efficiency. So, it says like increasing the turbine entry temperature, basically it is reducing our thermal efficiency, it is reducing our overall efficiency even for the flight condition. Okay. So, now the situation is whether to go with this turbine entry temperature to be higher, at what cost you need to be careful about. Okay. Now, let us move with the next, that is what we have is a bleed. Be careful here for these numericals. For the ground condition, bleed point we have taken, it is at some pressure and temperature. Same pressure and temperature we will not be achieving for the flying condition, and that is the reason why bleeding it was done at some other pressure and some other temperature. So, do not get confused with those numbers. So, let us try to look at what is happening with the percentage bleed change. So, here we are having 20%, that is our design condition. So, when we are increasing our bleeding, it says we will be having reduction in hot thrust. There is not much impact because it is not having straight impact on fan configuration, that is the reason why my cold thrust will remains constant. So, with increase of percentage bleed, basically we are decreasing our thrust. Okay. So, this will be the same condition both for ground condition as well as for the flight condition. Since my thrust is reducing, we will be having reduction in the specific thrust. Okay. for both ground as well as for the flight condition. Now, let us try to look at what is happening if we are increasing the effect of bleed, or we are increasing the bleed by percentage, and it says we are having say negligible effect on thrust specific fuel consumption, but you can say bleeding has more impact on the thrust generation capacity, and that is what will be reflecting in terms of our efficiency. So, it says for the ground condition, with the increase of percentage bleed, our thermal efficiency will be reducing. Similarly, for the flight condition also, with increase of bleed, we will be having reduction in thermal efficiency, we will be having say reduction in overall efficiency. With increase of percentage bleed, it has slight impact on propulsive efficiency. Okay. Now, let us try to look at this is of our interest. When I say the aircraft, it is flying at some Mach number. So, flying condition we will be discussing. Let us move from say flight Mach number of 0.3 to say 1.4. We know it is not possible for our commercial aircraft of that too of this size to move to this Mach number, but let us see for the sake of calculation in order to understand what is happening. So, here if we look at with increase of flight Mach number, the hot thrust, that is what will be going to be decreased. Same way cold thrust also is decreasing up to certain Mach number, and later on that is what is going to increase with the increase of Mach number, and this is known to you the reason behind this, why we are flying at high altitude, why we are flying at high Mach number. We have discussed all these things in our basic fundamental lecture. So, it says with the increase of flight Mach number, we will be having decrease of net thrust. Okay. Now, let us look at what is happening with the specific thrust. So, when we say my flight Mach number is changing, here in this case my mass flow rate also will be changing, and that is the reason my specific thrust, that is what will be reducing with the increase of flight Mach number. Okay. Similarly, here if we look at my thrust specific fuel consumption with the increase of flight Mach number, that will be increasing. Okay. So, this is what is in line to what all we are discussing in terms of thrust, specific thrust, and we can say thrust specific fuel consumption. Okay. Because when we are flying at higher Mach number, in our thrust equation we have our terminology, that is what is V infinity, and this V infinity at that particular height will be having more impact on thrust and your mass flow capacity. Okay. So, here in this case it says with the increase of flight Mach number, it has slight impact on the thermal efficiency, but it has great impact on propulsive efficiency. So, when we are flying at higher Mach number, our propulsive efficiency will be increasing. That is what is giving the indication for flying at higher Mach number configuration, specifically for our say high bypass ratio engine, that is what we are using for commercial aircraft. It says with increase of propulsive efficiency, we will be having rise of overall efficiency. Okay. So, this all will be giving us the indication in terms of what all will be the effect. Now, the similar kind of plot you can put by taking different turbine entry temperature. Similar kind of plot you can repeat by taking different overall pressure ratio. We will be discussing very soon, where we say we want to optimize these results. We want to calculate, we want to find the optimum value of say fan pressure ratio, we want optimum value of compressor pressure ratio, we want optimum value of turbine entry temperature. Okay. And this all, that is what will be resulting into improvement of efficiencies and improvement of specific fuel consumption. Okay. So, as we move forward, we will be discussing as and when required. Now, let us discuss what all we were discussing in this week. So, here As we have discussed, this is Pratt & Whitney 4000 series engine. Again, let us look at, we say we are having larger size fan, it is 2.8 meter. Okay. That is what will be connected with the compressor. This is my booster compressor, or you can say intermediate pressure compressor, or we can say LP compressor, and that is what will be run by the LP turbine. Now, let us discuss something in a different way. Here, if we look at my LP turbine stages seems to be more. Okay. Now, let us discuss what all we were discussing in week 2, where we have discussed if I am increasing my polytropic efficiency, my turbine efficiency will be increasing. What is the meaning of that? It says if I am increasing my polytropic efficiency, it means if I will be increasing my number of stages for the turbine, that is what will lead to increase my efficiency. Okay. Now, the situation is we know our performance of the engine, it is depending on the efficiency of these turbines. It depends on efficiency of both HP turbine, LP turbine, as well as it is also depending on the efficiency of compressor, efficiency of LP compressor, efficiency of HP compressor, efficiency of fan, efficiency of combustion chamber. Now, let us try to look at, so what is the meaning of that? It says if I am improving say or increasing the number of stages, I will be improving the efficiency of my turbine. Where will it reflect? It will be reflecting in terms of my overall efficiency. That is what will be reflecting in terms of my specific fuel consumption. Okay. So, we can say we will be putting more number of LP turbine stages. Let us move here in terms of say compressor. What we have realized, if we will be going with say increasing the number of stages, or we can say if we improve the polytropic efficiency with the increase of pressure ratio, my efficiency will be going down. So, that is the reason it says like we need to go with low number of stages for the compressor. Okay. Now, here if we look at this compressor stages, they are at smaller diameter, this compressor stages are at higher diameter. Okay. Now, what could be the reason? When I say I am increasing the number of stages of LP turbine, means I will be extracting less amount of work by per stage. So, per turbine stage it will be extracting less amount of work, and that is what will be helping us in order to rotate this wheel at lower speed. Now, the question is, do we really want to rotate at lower speed? The answer is yes. What will happen? Suppose if I consider this is my blade. For this blade, if I am moving on say towards the tip region, then my u, what we say as peripheral speed, that is what will be increasing with the increase of diameter. And if you recall, we have discussed, it may happen that my flow will be going transonic or supersonic in this tip region. Now, when my flow is going transonic or supersonic in that region, there will be formation of shocks, and we know shocks, that is what is generating the aerodynamic penalty, or it will be increasing the losses, and we do not want to increase the losses because we are concerned with the efficiency. Okay. So, if we are having less losses, we will be having good efficiency. So, what is the meaning of that? I will try to rotate this wheel in such a way that my flow will not go towards very high supersonic flow. It may be nearly transonic, that is what will be okay with. That means, I need to, one idea is to increase your diameter of the fan, and second idea is to say decrease the rotational speed of this wheel in order to achieve same compression ratio. Okay. Here in this case, you can say here what we have, my diameter is coming to be higher, it is not that aesthetically we are having this engine is looking fine. Just realize how the designer has made his thought process. Since my rotational speed for this disc it is lower, and in order to achieve the high pressure ratio we have increased the diameter. Okay. Similarly, suppose say if you look at this CF6 engine, what is the case if you look at we are having more number of LP turbine stages. Just look at same way we are having more number of say my compressor stages. Okay. And here this is my HP turbine, that is what will be having 1 or 2 stages. So, there is no issue here. Now, the question will come, say what about the cost of this engine? What will happen? Since I am increasing the more number of turbine stages, that is what will be increasing the number of blades both for rotor as well as for the vanes. That is not preferable, because that is increasing the length of the engine, that is increasing the weight of the engine, that is increasing the cost of the engine. So, now the question will come, what is the solution for that? Yes, what solution? Do you have any solution for this kind of query or this kind of question mark? And that is where the research and development activity, that is what is going on, where we want to reduce the number of stages for the LP turbine, okay, and we want to rotate our wheel at lower speed. One more observation from last numerical, if you look at it says if we are increasing our bypass ratio, we will be able to increase our propulsive efficiency. Now, this propulsive efficiency, that is what will be reflecting in our overall efficiency. That means, it says you increase the diameter of this fan. Now, the question will happen, if I will be increasing the diameter of my fan, there are chances that my whole casing that will be touching to the ground. Okay. That is what it says, bypass ratio of 10, 12, 14, 15, you can move ahead, but the thing is that is what is creating trouble in fixing the engine on the aircraft. Okay. So, that also is asking for some kind of solution. Can we go with very high bypass ratio? One more thing, if you look at when I say I am increasing, suppose my diameter I am putting same here, this fan diameter I am putting same, and in place of having this bypass ratio to be 7, I will be going with the bypass ratio of 10. What will happen? My core engine dimensions will be changing. Is it possible to go with that? Yes. Okay. Similarly, we have discussed about this configuration, where we are having our fan and say LP compressor, that is what will be rotated by LP turbine, and we are having centrifugal compressor. So, you can say what all query we were having with the number of stages for the compressor, that has been rectified by using this centrifugal compressor. But now, the question is what need to be the diameter of this wheel, because suppose if I consider, if I am applying my equation, what equation we were discussing about the Euler's equation, what it says, my compression capacity, that is what is a function of my diameter, or we can say it is a function of peripheral speed. If I am looking for this dimension to be smaller, that means I need to rotate this wheel at very high speed. If I will be rotating at very high speed, that is what will be reducing the dimension of this compressor. Okay. And if that is the case, here in this case we can say we are having number of stages, that is what is lower. But at the same time we were discussing about the Safran engine, where we are having booster stage, we are having say axial compressor followed by the centrifugal compressor, and then we are having more number of stages. It says almost 4 LP turbine stages. So, now the thing is we are looking for the next generation engine, where we will be having weight to be reduced, because that is what will be giving the benefit in terms of reduction of drag, and that is what will be reflecting our improvement of specific fuel consumption. Okay. Weight, size, length, that is what are coming as major parameter. These are the major parameters for the future engine. So, you can say at initial stage some thought process it was there. Later on people they started moving towards say the improvement in terms of specific fuel consumption, improvement in terms of efficiencies. These days people they started talking about net zero. Now, what is the meaning of net zero? You can say you will be having everything that is what will be working efficiently, so that we will not be having the exhaust with higher carbon content. Okay. So, ultimately it is nothing but net zero or moving towards net zero is to make this engine as efficient as possible. Okay. So, we will be continuing our discussion on all these aspects in next coming weeks. So, here we are stopping with just make a thought process. Suppose what all we were discussing or we have discussed today, how do we move forward with? Just try to put some more efforts in order to understand these questions, and we will be discussing the solution for these questions. Thank you very much.